Okay, hello again. I am Gerardo, and I'm going to talk about the numerical simulations of structured jets in the context of short gamma ray burst. Specifically, I will to present a study of of what is the most important element in the jet launching in order to obtain a structure of the jet, and what is the implications to large scales. I will to start with a general picture of my talk. So in the context of neutron star merger, a powerful jet is launched after the neutron star merger. This jet contains a very high velocity, relativistic velocities, and in the central source or in the central engine, there are many elements which can structurate the jet, such as the magnetic fields, structure of accretion disk, or structure of material of debris of the neutron star merger. So an intense flux of neutrinos driven a wind of debris, and within this wind, the jet start to propagate. Right, in the first millisecond, the jet reach the boundary of the wind and acquires an external structure. It's called the cocoon, external cocoon, which is expanded more seconds after when the central engine is turned off. It's already turned off. The external cocoon is converted in a shell, and it's expanded. They have expansion in an external interstellar medium. It's important to remark that since the discovery of first GRP of axis, the GRP 17017A, the study of structured jets acquiring a relevance because these objects can explain the observation of four off-axis observers in the afterglow stage. So in my next slides, I will present the study of propagation of structured jets at small scales in this phase. And finally, I will to present how is the afterglow radiation from the final structures of these jets. So here I will present a little background previously to my work. So in the context of the neutron star mergers, there are many interesting jobs about numerical simulations, and the results of these people can help us to understand the initial conditions of the jet launching. Another interesting studies, for example, of the Ariadna Murguia, has performed interesting simulations with the implementation of top hat jet in the structure neutrino-driven wind. And she obtained a better, interesting or a more realistic structure, final structure of the jet. For other hand, in the context of GRV 17017, the group of Davide Lazzati explained the data of this GRV from the final structure of the top hat cocoon extended to large scales. This is a repercussion in large scales. It's important to remark that there are a lot of studies which explain the interaction of top hat jet with a neutrino-driven wind. However, these studies includes only the top hat jet, right? And but in the central source, there are elements which structurate the jet. So this is the hypothesis of our work. In our work, I present a new study of structured jets interacting with a neutrino-driven wind, spherical neutrino-driven. So how is the implementation of our structured jets? First of all, we choose three different profiles of luminosity, which depends of angular variable. So also the velocity depends of this function of theta. So we choose three different profiles from more commonly made jets. This is the top hat jet, is the more commonly made jet without structure, is the typical top hat jet. And another more extended jets, like a Gaussian profile and a power law profile. This is more extended jet. And also, the jet has implemented at a distance about 10 to 8 centimeters, sorry, and with an initial Lorentz factor to 20. There, we have performed several simulations, about 22 simulations, with the change of parameters, of fixed parameters, such as the luminosity with two values, high and low, and three different times of injection for the jet. A short time, about of breakout, a medium time 1.5 seconds, and a large time to 3 seconds. This time we are carefully with this time. This time I constrained with the duration of short gamma ray burst. So this is an example of simulations and comparison between top hat jet in the left and structured jet in the right. Previously, a wing is expanded and the jet starts 1 second after. 1 second after. The jet acquires an external cocoon and continues with the expanding to the external medium. The time of integration is 10 seconds. Is enough to follow the final structure of both type of jets, both hat and structure. In this slide, I show you a screenshot of the first seconds of evolution of the jet. In the upper panel, I present the jets just in the time of breakout. Here in each panel, I present in the left side the low luminosity jet and in the right side the high luminosity jet. The difference between them is that the high luminosity jets and structured jets acquire or present a shield which expand the material to more extended regions. So this is in the bottom panel. I present the jet evolution 3 seconds after their launching, and the cocoon is more extended for the high luminosity structured jets, and is less extended for the low luminosity jets. So here I show you the final structure of the cocoons. In the panels in the right side, I show you the density maps of final cocoons, and in this final output of my simulations, I perform calculus of the final energy, or the energy per solid angle in a post-processing. So each color represents a different jet profile. So this is the final structure of every jet models for low luminosity jet models. And this is important to remark that the structure of the jets is preserved. So if you put in the initial conditions a mercury made jet, ends in the final cocoon ends more collimated than the structured jets. So the effect of the time injection is more expanded jets and a more bigger peak in the central in the jet axis. So For final structure of high luminosity jets, it's more easy to distinguish between them. The top hat jet, it's the black lines, ends more collimated, and structured jets ends more extended. And it's also it's important to see that in the final cocoons for top hat jet get an important amount of hydrodynamical instabilities near to the jet axis. This probably in this zone appears an important mixing of baryonic material and then instability and the hydrodynamical instabilities can expend important energy for important energy which can expand in the jet propagation. The better models for explain short GRBs are structured jets because the shield implies that the material is expanded in the high latitude regions, and this helps us to a good propagation of the jet. Finally, I want to introduce to large scale implications. So it's important to remark that with the previous results, we can find that the implementation of structured jets, it's important because you obtain a different jet dynamics in the final structure or after the jet breakout. So in this picture, in this square, in the left panel, I show you a picture of a final structure of some model.
Gerardo, you have 2 minutes.
Thank you. So in a post-processing, we take this final structure and extrapolate to large scales, about 10 to 16 centimeters. It's a scale about of afterglow stage of this, and with the spectral shapes of synchrotron radiation, and from the output variables, output hydrodynamical variables, we can obtain different light curves for distinct off-axis observers. So in the right panel, I show you the differences between the light curves or the light curves of TINET from final cocoons of different jet structures. So in the first panel, I show you the top hat jet, the final light curves from top hat jet, and the difference are evident with the final light curves of structured jets. There are important difference between in this part after the first increment of light curves. We obtain a more smoothly increment, which is consistent with another previous models of structured jets. And in the future, we can predict new off-axis objects with these models. So this is my conclusions. After the breakout, the structure of the jet is preserved. This is an important point because the implementation of structured jets implies a different jet dynamics, and at the larger scales, we can obtain strong consequences in the light curves for afterglow stage. My part, that's all. Thank you.
Thank you, Gerardo. There is a question of Diego for you. Diego, you can ask.
Okay. Hi, Gerardo. So, what what differences or what would doing your simulations in 3D, how would the 3D affect your results?
The 3D, well, yeah, with the 3D simulations, you can obtain also effects. First of all, you can, these simulations are symmetric, and with the 3D simulations, you can obtain jets without symmetry, with a loss of symmetry.
Mm-hmm.
And the results change also in the instabilities in the center. You can obtain a different values.
Okay. So do you expect in 3D for global morphology differences or not in 3D compared to yours?
It depends of the implementation. In our jets I implement a powerful central core, and in the 3D simulations I will put a similar central core, and the core of the jet will be the same. For the morphology of the morphology in these angles, maybe can appear with important difference.
Okay, thank you.
You're welcome.
Can we move to Robert for another question about magnetic fields? Robert, you can ask your question. Anyway, so the question is, do you account for a possible role of magnetic fields in your simulations?
Magnetic fields?
Yeah.
Maybe in the future. The effect of the magnetic, for the mescal code in this time, don't solve magnetic fields in the relativistic case. So in the last months, there are an important discussion about this point. The effect of the magnetic fields over the jet evolution is about in the center of the jet. The importance of implementation for magnetic fields is they avoid the numerical, the hydrodynamical instabilities in the center. The magnetic fields produce an intense flux, the intense vector pointing flux, and this pointing flux generates an intense core, and the structure produced with magnetic fields is like two-side jets, and this is the most important element, and you can obtain more expanded cocoons. Tomorrow, Leo Garcia will present the effect of magnetic fields imposed in
the discussion.
Yes.
Perhaps we can have a last question from Raphael, if it is rather quick. Raphael, can you summarize your questions?
Sure. So you argued that the interaction with the cocoon does not change the structure of the jet, right? If you launch a power law profile, it ends up as a power law profile. If you launch a Gaussian jet, it ends up as a Gaussian jet after the interaction. Is that correct?
Yeah.
And so therefore, would you conclude that the final structure, I mean, after interaction, and therefore all the afterglow emission, etc., is mostly determined by the physics of the jet launching at the level of the accretion disk? I mean, and before any propagation in the cocoon, therefore.
Yeah, the structured jets are parameterization of the effects in the central source. For example, in this case, in these simulations, for example, the magnetic field can structurate the jet, can maybe can produce a more extended jet. the typical studies has been performed with the top hat jet. So with the initial structure of the jet plays a more realistic dynamics because the jet start with material spread at angular in angular sites, and our results show that if the jet starts more spread, ends more spread, and the consequences in the large curves are perceived in this part.
Thank you.
Okay. Thanks.
Thank you, Gerardo. So we move to the next talk with Roshan Jaisinda Data 3 about inferring the structured jet profiles of GRBs. So it's only 5 minutes, so I will not say anything because it's too short. So